the cloud. So a small but enthusiastic group, but I'm 1/3 of the group who's online because I count as two. One of the laptop is one, and my main computer is the other one. Yeah. So I feel very strong being, 1/3 of the whole class. One thing I wanted to just mention, that the homework is out, the first homework. You're welcome to take advantage of the office hours. And I'd like to remind you that those of us who would like to get credit for this class, you have to turn in all the homeworks in time. Reason being is that will be a written record of your answers, and we will be asking you those of you who want to take the class for credit, to explain one of your randomly selected solutions in the oral exam. If you haven't turned in all the problems, then who knows whether you randomly select the solution that we randomly select the problem, and we'll see what your solution was. But if you have no solution to it, then there's nothing you can explain. So I'm just seriously, please mind the deadline, and up till the end of the day, just send in the PDF to the teaching assistant of this class. Are there any questions about the logistics of that? Any further questions? I anticipate a total of maybe 5 homeworks. And again, the office hours are there to answer your questions, should you have any. Now, so this is where I was last time. We were looking at, I'm really wrapping up the part about chaotic dynamics. And remember, the way we would define that the map is chaotic is that we would show that in some sense it's equivalent to a prototype chaotic map. And the prototype chaotic map is the Bernoulli shift map, which has all these desirable properties that we have been discussing, right? And I've done examples in which perhaps that exact equivalence doesn't hold. There's only a semi-conjugacy between the two maps, but that's sufficient as long as the semi-conjugacy still holds on an uncountable set of trajectories. So the possible duplication, double encoding of motions through symbolic dynamics is restricted to a countable set. We then did the generalization, another generalization, not just in the way of looking at semi-conjugacies, but we asked the question: how could we? Is there only one kind of chaos, or can there be sort of a hierarchy of chaotic systems, one sort of more chaotic than the other, or different types of chaos? And the answer is yes. And this is one sort of generalization, or actually a couple of generalizations we looked at, is that we can enlarge the symbol space itself in which we encode the dynamics, okay? So instead of just having 2 symbols, say 0, 1, or 1 or 2, you can have a whole array of symbols, n of them, right? Say varying from 0 to capital N minus 1, but you can actually have infinitely many of those as well. And that would be some complexity, right? And then you can still have a double infinite sequence built out of these digits. Another very frequent generalization that's needed is that there are sometimes constraints on the admissible sequences. So in other words, you cannot just have an arbitrary prescription of symbols because they will not be materializing in an actual problem. And you have to have a way of excluding the ones that cannot arise. Why do you want to exclude them? Because you don't want to reach conclusions about the complexity of a dynamical system by using another one which has a whole lot richer dynamics than the original one. And you're making statements about the richer dynamics, and it turns out that many of those statements are irrelevant for the original dynamics. So you want to take care of that already at the stage of encoding. And you only want to use a symbol sequence, a symbol space in which all the symbols really correspond to possible behavior in the real system, okay? That's the reason for this. And one way of doing that systematically was to introduce a transition matrix. And a transition matrix encodes the possibility of you going from state I to state J. Namely, you build the matrix will be 1 at its ij element if the transition from state I to state J, whatever states you're encoding, is possible. Otherwise, that matrix element will be 0. And then this will be then part of the definition of the space. We talk about this symbol space on n symbols, right? We transition matrix A whereby you have these general symbols as here, but you're restricting these symbols to those in which the Si and Si plus one after another, is admissible. In other words, you only include symbols here for which the corresponding entry in the transition matrix, so that adjacent digits are consistent with the corresponding entries of the transition matrix. And we talked about the fact that you can easily overdo this. I can describe this transition matrix, so only 1, 1, and 2 transitions are possible. But by doing so, I kill off the dynamics even in the space that we've already seen, the space of 2 symbols, right? Which used to be a Cantor set. All of a sudden, it's just a set of 2 points, 2 infinitely repeating 1s or 2s. So it's by no means obvious that if you take a system and you manage to encode it in real life, then, and now you allow for a transition matrix of any kind, it's not by no means obvious that you're getting some sort of rich dynamics. You can get very boring dynamics, okay? You're using symbolic dynamics, but the outcome is not chaotic. So the term for the shift map on such a symbol space is a Bernoulli shift map of finite type. Finite refers to the fact that we're still using a finite number n symbols, and the transition matrix is A, okay? And we had an important theorem that says that if the matrix is irreducible, meaning that there is a power to which you can raise this square matrix such that all elements of that powered matrix are non-zero. So at the end of the day, all transitions are possible if you wait long enough, that is the case. Then the space is in fact a Cantor set, and the shift map on that space, even though you've decimated the original space, even though you have put on constraints, right? That not all sequences are admissible, yet you have enough left so that they have diverse enough dynamics that we require for chaos, which was sensitive dependence on initial conditions, topological transitivity, and density of periodic orbits, right? But again, the matrix has to be irreducible. And I just made a case for that here, that actually does mean what I've just said, that if one of these powers, or if all of them are non-zero, then these triple products, for instance, for 3, when you sum them up, at least one of those products has to be non-zero. And that means that when this particular one is non-zero 1, that there exists a K and L, so that you can go from I to K, then to K to L, and then from L to J, right? So ultimately, you're able to spread from any particular state to another one. And then we went back to the original example that came out to give trivial dynamics, and checked, and sure enough, the matrix there was not irreducible, because it doesn't matter how many times you multiply identity by itself, you still get identity, which is not reducible. It is not irreducible because you have these 0 entries forever, right? So I want to then take this idea and show an application, but I also want to show an application which is outside the circle of what we've seen so far, examples in population dynamics and mechanics. And I think this was a very important motivating application when this was described in the literature, because people have realized that chaos is real around us in many ways, in unexpected places where you would expect it to see the last, yet it's still there, right? And this was basically, the general area goes, I think there may have been even a book under this title, Chaotic Numerics. So numerical procedures can in fact be chaotic, even though they are not designed to be. And it's not necessarily because you coded them up incorrectly, it's just the nature of the beast. So this one example that I want to get to and describe in some detail, I think I'll give you an introduction, but then I would rather walk you through the example in my notes, because there are pictures that are tedious to draw. I used to draw these on the blackboard, and it took me maybe a lecture and a half to get everything right. So I'll just go slowly and walk you through the notes. So this example goes by the title of Chaos in one of the most important zero finding algorithms that is used nowadays all over the place. It's the Newton-Raphson iteration. I'm only going to discuss here the one-dimensional version, but it works in very practically same idea in higher dimension. So what this does, so I'll just abbreviate it as NR. So NR is basically finds the zeros of nonlinear functions by iteration. Anything that you can phrase in terms of iteration is very convenient because it's very easy to make it algorithmic. You just repeat, you write a cycle, right? But it's not clear a priori how a zero finding procedure can be phrased as an iteration. So this idea was quite an important one. So let me draw a picture that shows the idea of Newton-Raphson in 1 dimensions. So this is 1D. So also works in any dimensions. So in 1 dimensions, if this is x and you have a general nonlinear function, this will be y, and I'm drawing the graph of that function, say in blue, like that. So this is the graph of f, okay? And somewhere has a function that I'm after, 0 that I'm after. Then if you are able to locate a region in which the function changes sign, then there's a very efficient procedure to zoom in on the 0. So suppose you're on the one side of this. So you pick some initial guess for the 0, which of course will not be right. You have no idea where the 0 is. It doesn't matter which side of the 0 you're on. You just fix an initial condition. And what you do, you evaluate a function at that point, which is here. And then you draw a tangent to it. So very important, the function has to be differentiable, okay? And you replace the tangent with that curve. And so the equation of that will be this new function that you pass to the gx equals, I'm just writing down literally the equation for this line. I evaluated the function, and that's the value f of x, x naught. And I'm adding f prime x naught, x minus x naught. So that's the equation of that line, okay? Now for that line, you can explicitly find the 0 of that line. And the 0 of that line will be this point here. I call that x1. So the definition of x1 is that I take this function g and I solve it for x1. I look for it 0. And this is easy to do because it's a line, right? So from this, you get the explicit expression for what I'm going to call x1. And that's x naught minus f of x divided by f prime of x, but it's not x naught. So that's an explicit expression. And then you repeat the same procedure at that point. So you evaluate the function right there at that point, which is here, okay? And then you replace the function with its tangent. So just, again, the function has to be differentiable, okay? So f has to be c1. And again, you follow the same procedure that now you're looking for this new replacement to the function. You're looking for the 0 of that new replacement. And again, since it's a linear function, you can explicitly solve for what we call now x2, right? And so on, you keep doing this. You go up there, and again, now you're taking the derivative here. Okay, and maybe I just draw one more thing here so it becomes clear to you, right? So this is then the procedure. This is how you keep going. This is geometrically the procedure, okay? So if this was x1, this was x2, then in general, the recursion that you build, it's important to see that once I'm in the second step, so I'm doing this again, I use the exact same formula that I used before, except because all I'm doing again is I'm drawing a tangent to that curve and to that function, and I'm simply solving for the zeros of that line. So it's the exact same formula that I keep applying. So generally speaking, I will have xn plus 1 equals xn minus f now xn divided by f prime xn. And we can just define this as a function. It's a nonlinear function acting on nxn. And this is the formula for the Newton-Raphson iteration. You can imagine this to work in higher generality as well, except that the derivative will not be then a single scalar value, but it will be a derivative tensor, a Jacobian. So I'm missing the prime there. So you can't write 1 over that, but you will have to work with the inverse of that. So that has to be non-degenerate. The same here. I mean, the way to evaluate you can only evaluate this function here, this n of xn, and this defines the Newton-Raphson iteration. You can only evaluate it as long as this quantity here is non-zero, right? Because then it blows up. So it does assume that you're at a point where f prime of xn is non-zero. Otherwise, you're blowing up. I mean, numerically, you can safely assume that, right? Even if your function has 0 derivatives, what is the probability of you ever hitting that exactly the point where it has 0 derivative? That's 0. Because don't forget that also you have just a finite number of digits to store any value on the computer. So if your function has a 0 derivative at square root 2 or at anything that needs more digits that you're storing on the computer, you will not get to it anyway, right? Exactly. So there's multiple reasons why this is a restrictive assumption. Now, why are we doing this iteration? We were doing this iteration because of the following observation. So 2 things to observe is that if we find that this discrete dynamical system defined by this iteration has a fixed point somewhere, and that's what it means for this discrete dynamical. So this is a discrete dynamical system, right? One-dimensional. So if it has a fixed point, what does that mean? Well, for you to have a fixed point, this must be equal to that, right? Now, f prime is regular. There's no problem with that. It's not going to go to infinity or anything. So the only way this can be equal to that is that this must be 0. But the only way this fraction can be 0 is that f must be 0 there, okay? And that's precisely what we've been looking for. So there is a one-to-one relationship between what we've been looking for, the original object, which is zeros of the function, and fixed points of this iteration. That's why it makes sense to iterate to get there. Well, to be honest, it only makes sense if that fixed point is attracting, if it's stable, because otherwise you will never get to it. It's technically a fixed point, but you're not better off doing this iteration if you're avoiding it and you're being repelled by it. You will not. The idea is that you should be actually accumulating on it. Now, in the picture that I've shown you, that seems to be the case because I started from x0 and then I go to x1. And with this construct, I seem to be zooming in on that 0 right here. But that just might be the picture that I've drawn, right? What is the general condition for this procedure to converge? The beauty of discrete dynamical systems that, this used to be a numerical analysis question. And when I first, certainly, and I'm sure many of you, when you heard about convergence of sequences, you looked at it as a tricky algebraic problem. Maybe somehow you can take that limit, maybe if you divide it. But once it's phrased as a discrete dynamical system, then it becomes a dynamical systems problem, right? And the question is, does it have a fixed point? And if yes, what's the stability type of that fixed point? Okay. So how do you find out about the stability of this fixed point? Well, it's a one-dimensional dynamical system, and we need to take it, we need to linearize it in principle at that fixed point, right? So we need to take the derivative of that at the fixed point, which just means that I need to take this derivative in general, okay, and then plug in the fixed point. So when I take this derivative in general, I have to take the derivative with respect to the argument of this n function. So when I take that derivative first, this term gives me 1, okay, minus, and here I just use the quotient rule of differentiation. So that will be f prime, and I only plug in x naught tilde. But I have to shift this a bit because I think I'm getting too close to that equation. So f prime x naught, but I bar. but then I need to multiply that. That's also in the denominator, so this will end up being squared, right? Then I have to subtract f, again, x naught tilde plugged in, second derivative of x naught bar, right? And then divide by f prime at x naught bar squared. Okay. Now, don't forget that x naught bar is a fixed point, which means that it's also a zero of the function fx naught, right? At which point you can conclude that this term here is zero. And if that term there is zero, then this term and that term, those two factors are equal, which means that their quotient is 1. So you're subtracting 1 from 1. So that's actually 0. Now, if you do stability analysis in a continuous setting and you get 0 while you're calculating the stability of your fixed point for a continuous dynamical system, then you're out of luck, because that means neutral stability type under linearization, and that's inconclusive for a nonlinear system. Luckily, we're not in the continuous setting. We're in the discrete setting. And remember, in the discrete setting, that's what I discussed in linear dynamics 1, also to some extent in linear dynamics 2. The magic line is not the imaginary axis. The magic line that decides about stability, whether you're stable or unstable, meaning whether you're on the left or right-hand side, that translates, when you talk about discrete dynamical systems, is to the unit circle. Because in a discrete dynamical system, the linearized dynamical system, the linear operation means multiplication, repeated multiplication by you get what you get as an eigenvalue. So if that's less than 1 in norm, then you're shrinking. If it's larger than 1 in norm, then you're growing. So the magic line is the derivative or eigenvalue or the derivative in 1 dimensions being 1 in norm or less or bigger. The magic line is now a circle. So in that sense, this is as small as it would ever get, right? Because in norm, 0 is the smallest number that we know of. It's very interesting that this is a good thing in the discrete system. It's actually a very good thing. It's called, that the fixed point, it's called superstability. And again, we need to reprogram our view when we talk about discrete systems. In a continuous setting, 0 is a bad thing, but in a stability analysis setting. But here it's a good thing. So how good is that, or why is that? To get some sense, if you haven't played with maps that have this property, let's just quickly draw a little bit of sketch, and then I'll take a closer look here. So if this is if this is a one-dimensional mapping, then we can just iterate it in this using the cobweb diagram, right? And I will just use as illustration as a little piece of that map. So assume that I have a fixed point, say here, okay? And assume that the graph of my map is such that it has a 0 derivative there. This is supposed to be 0. Okay. Right. So if I then go ahead and try to iterate in any situation like this, because of that particular geometry, my map is very flat nearby, so to speak. And that flatness will force me, when I do the cobweb plot, to converge super quickly. See, I can maybe do 2 steps and then it becomes indistinguishable from what I see. That if I start from the other side, the same thing. I start from here and I draw a horizontal line, okay? And I'm pretty much there. Again, I can't go anymore further. I can't even really resolve it well in my diagram. Maybe this very same function has another point where it has another fixed point where it actually has a cubic tangency with 0, like that. Okay, so this would be another case, which also obeys the superstability designation. And again, try that. I mean, I can't even do justice to that. I tried the iteration with this case in in this case, maybe the way I get on the other side, and then I get lost very quickly. And again, somehow, because the function is so flat, basically that I have a hard time getting away. Now, that's hand waving though. Can I actually say something more analytically about this super stability? Or why does it imply a very quick convergence to the fixed point? So the reason is that near a fixed point, x naught tilde, I'll just do a Taylor expansion. I can do it because I assume the function is smooth. And I will specifically do it for the Newton-Raphson iteration. But what I'm doing now is true for any function that would have a fixed point with a zero derivative. Okay. So how do you do the Taylor expansion? And x is near. So this is much less than 1, right? In norm. So I just evaluate the function at x naught bar, because that's the basis for my Taylor expansion. Then I take the first derivative at x naught bar multiplied by x minus x naught bar, right? Plus 1/2 and double prime x naught bar, x minus x naught squared, plus order x minus x naught bar cubed. So this is what I have here. Now, n x naught bar, since I'm doing this near a fixed point, this is the same as x naught bar for forever, just to know. And my assumption is that this is, well, I concluded it for n, but generally speaking, the assumption behind this picture, which was not just an assumption, but a conclusion for n, was that this is 0. So that would be that. So this is the reason for this is fixed point, and the reason for this is the superstability. That's where I'm using it. Okay. So then if I rearrange this a bit, then on this side I will have nx, and here I will have nx bar. Okay. And on this side, this is, if I take the norms, then this will start out like n double prime x naught bar, x minus x naught bar squared plus order x minus x naught bar cubed. And this is where things become clear. Now, this would be, for a general iteration, you can also iterate any other, you can also Taylor expand any smooth iteration function formula near a fixed point. But in that case, you would get a sizable contribution from here, something, if it's not super stable. Of course, the smaller the better. If this is a small number, we like that, presumably, because it's stronger stability. But in the case of a super stable fixed point, this is completely absent. So there's no linear term, only quadratic term. And people, call this type of a phenomenon is the super fast convergence, or quadratic convergence. And that's a very good property to have. It means that in one step, if you have a reasonably good approximation, say your order epsilon close, right? Then in one step, you're going to be order epsilon squared close, which means one order of magnitude just in one step. And that's not a property of a general iteration. You can be happy if it shrinks, but you're not going to do it by an order epsilon, right? Just imagine your initial distance is 0.1. In one iteration, it becomes 0.01. In two iterations, it's 10 to the minus 4. In three iterations, 10 to the minus 8, right? That's called superconvergence, and for a reason. That's why the Newton iteration is an incredibly good procedure. It's very efficient, right? When it works. Now, does it work? Well, generally speaking, it does work, but sometimes it doesn't. And people wanted to understand why that's the case. So very fast when it works. Now, we now have a better understanding using dynamical systems terminology. What does it mean for it to work? I mean, it's not sort of a random outcome We know exactly when it works. It works when your initial condition is in the domain of attraction of the fixed point. If it's not, then who knows where it's going, right? Might be going ultimately to another fixed point, but it has to be in the domain of attraction of a fixed point. Right? Now, if it's not immediately in the domain of attraction of something, then it has to be in the domain of attraction of something else, otherwise it will never converge, right? Can that happen? That, all right, here's one fixed point, and I'm not technically in the domain of attraction of that, but all right, but hey, the function may have other zeros, then I'll go to those, right? And then maybe I reposition the initial condition, and I will place myself then in the domain of attraction of the fixed point that I wanted to get. Can it happen that A, that I'm in nobody's domain of attraction, okay? And B, when that happens, what can I do? Can I just do, can I go crazy, or will I still be jumping on periodically? So that was a question that entertained people. And there was a very good, the paper based on observations, initial observations, iterations sometimes appear, okay? I should say may appear irregular in certain cases. So then a pair of authors looked at it in more detail, not in the most general case, but they looked at, actually, they just said, you know what, let's look at simple functions for which we actually even know the exact number of zeros, and the functions are analytic, not only infinitely many times differentiable. So this is a cute paper, Sari and Urenco. The reference is American Mathematical Monthly, which at least these days is not, necessarily your #1 research journal. It's more of a collection of interesting observations, but I find this paper highly insightful and influential. I think it came out in 1984. Here's the page numbers in case you want to look them up, right? And who actually looked at it, so analyzed it. Convergence, at least for fourth order polynomials. Part of the reason is that if you have a cubic polynomial, you don't need Newton-Raphson. You have Cardano's formula for the roots, right? So the first polynomial that really gives you a headache when you look for zeros and you need numerical methods in general is the quartic order. So they said that's the simplest possible root finding problem. And they figured, oh, maybe that's simple enough so that it will never happen that I get complicated dynamics. So let's see what they did. And this is where I want to switch to the notes that you already have. And just introduce some notation. Okay, so I'm just going to go through this slowly. So feel free to ask questions. Any questions so far? So here you go. So I'm already giving it away. It turns out that even for quartic polynomials, you can have chaotic behavior in the Newton-Raphson iteration. It's pretty amazing. What we're talking about is looking for the zeros of a function like this, which they have simply written in this factorized form. So we actually know what the zeros are. It's not a mystery. We actually manufacture this polynomial by taking 4 real numbers that are ordered in this fashion. They're increasing, okay? And you take these monomials and you take their product. So therefore, this is your polynomial. You know everything about that polynomial. You know the zeros, you can take derivatives, everything. So we know in advance, since these are the zeros, that for the Newton-Raphson iteration, each and every one of those guys is a fixed point, or the index I ranges through 0, 1, 2, 3. Right? So there's no mystery. We know in advance what we're looking for. That's the beauty of this paper. That, with all this knowledge, you wouldn't have so many sort of funny thing happening. And as already stated, that's equivalent to having a 0 for this function. It's the same thing. So this is the phase space, or no, this is the phase space for this one-dimensional dynamical system that we're looking at. And we will be restricting attention to the span of the zeros. So remember, the smallest zero is x0, the largest zero is x3. So we will be looking at iterations of this map. It will turn out to be enough over the x0, x3 interval. So here's x0, right? Here's x3. Those are the two values. Same down here. And same here. So this will be x0 in this direction, and that's x3. So here's the phase space. And I'm setting up this picture just for iteration over that phase space. But in order for us to analyze this, we will need some other quantities that arise. Those will be A0, B1, A1, B2, A2, okay? Before I get to that, I just indicate that we know already the zeros of the function, hence we know already the fixed points of the map, so I'm just showing them here, right? On the 45-degree line, fixed points of a one-dimensional mapping live on the 45-degree line. Okay, so this would be x0, x1, x2, x3, right? But of course, here they are in the phase space. The reason why I'm showing these zeros here is that I know a priori that the graph of this function, the iteration function, has to go through these points. I don't know how that actually goes. I don't know yet, but it has to go through these points. Now let's see how that actually works out. I wanted to explain the choice of these A0, B1, B2, A2 quantities that will come out to be important. First of all, here's the function. It's a quartic function, right? And the largest coefficients of that quartic function is 1, because when you multiply these out, the leading order coefficient will be 1, which means that when you go to infinity, plus or minus infinity, you will be going to infinity with the function as well. It's not like a cubic parabola. Okay, so fundamentally, this is what I'm showing here, that after a while, the function will go to infinity in both directions, but in between, you're going to have 4 real zeros. Here's x0. And right at that point, right at the first point, because the function is coming down from plus to infinity, it will switch from plus to minus. And it comes back, switches from minus to plus to minus, from minus to plus, right? And these are the points that we already know. It turns out to be important to also give names to some other features of this graph that you're showing here. One of those features is the points where the function has 0 derivatives, and I will have precisely 3 of those, okay? The beauty of this construct that I never will have to fix these as numbers. Everything is general. Based on the geometry of this function, however, I know that there will be a point which I call A0, where the derivative switches from negative to positive, right? So this is the derivative of the function f prime, so it will switch from negative to positive there. Then the positive will gradually decrease and switch to 0. And that's why I'm saying for the derivative, again, comes down. So I will have another 0 here, which is A1. So this was A0, this is A1. And just track this function, the negative derivative again will switch to positive. So somewhere in between, I will have another 0 for the derivative. This is actually the derivative function qualitatively. So A0, A1, and A2 are the zeros of the derivative function as I'm showing here. It's good to remember that at those points, the Newton iteration actually blows up. Remember that. So those are the points that for which we are in trouble if you happen to hit them numerically, because at that point, this denominator goes to 0. So the whole iteration blows up. But once again, the probability of that happening is 0. That's why we don't care about that so much in practice. But when you start looking at details of the graphs of these functions, these will be handy to know. So that's an implication that at these points, the graph of the function, this is incorrect. It's not, no, it's fine. So the function itself goes to infinity, fine. And then I'm almost done with the new quantities. I just have to introduce one more set of quantities. And those will be the points where the derivative function has a 0. So wherever the derivative function has a maximum or minimum, that gives you 2 further points. These are B1 and B2. So these are points where the curvature of the function is 0. I guess the second derivative of this function. So the notation for, I will have 2 of these given the graph of this function, right? And because I will have 1 minimum and 1 maximum for the derivative. And at those points, the thing to know is that at those points, the second derivative of the function is 0. So if you scroll back to my calculation here, if the second derivative of the function is 0, that means that even though I'm not at, this was the derivative in general, this is the formula for the derivative in general, except you plug in x and not x on a bar. If the second derivative is 0, then this term is out. And this term, even though I'm not at a fixed point, it will cancel 1. So this comes out to be 1. This comes out to be 0, sorry, when I'm at a fixed point. But it also comes out to be 0, this derivative for the function, if f double prime is 0, right? Because then this term is out. These two add up to 1, and 1 minus 1 is 0. I'm just spending time on that to motivate that whenever that second derivative of the function is 0, the first derivative of the Newton-Raphson iteration function will be 0. That's what I'm showing here, right? And all I did here in this picture, I just took all these quantities that we have been introducing so far, A0, B1, A1, B2, A2, increasing order, and I have noted them here. If you want to note them on this side, then all you do, you come down here, and whenever you intersect these 45-degree line, you map them to the side, or to the other side, if you will. So these are just points that are good to be aware of, and in a second you'll see why they're good to be aware of. So next, I use these as aids to construct the graph of n in a general form. So what does that look? Because I need to be saying something about the iteration of n, and without the graph, the iteration of n, I can't think about the cobweb diagram. So at those points A0, remember, at all those points, the function blows up. Okay, and also if you check, the blow up happens in a way that it blows up when you come from this direction. It blows up to plus infinity. Okay, why? Because it's going to be f over f prime is responsible for the blow up. This term is bounded. So f over f prime, look what happens here. This is f, and this is what f prime is. And when I come from this direction, one of them is positive, the other one is negative. So their quotient will be negative, okay? But they are also featured with a negative sign here. That's why the blow up is to infinity, plus infinity. That's why I'm coming down from plus infinity. So this actually would go to 0. So it actually leaves this box here, okay? But I have chosen to work in this phase portrait. So this blow up, the function comes down, decreases. And the next point where the function, this is n now, the graph of n, will start changing. Shape is B1, because remember, B1 is the point where the function has a 0 derivative. This is the, this is f double prime. F double prime, but I'm pointing at the wrong thing. This is also the, at those points, f double prime is 0 and n prime is 0. So come down, and the n function, the iteration function, has a 0 derivative there. Then if you work through what happens there, there's a change in the derivative. So it starts increasing, but not for long, because it has to goes through this first fixed point, x1. Okay. Once it has come through this first fixed point, x1, there's a sign change in one of those quantities that determine the derivative of n. Remember, it's always here. And when you work through that, it just means that it will now go on and start decreasing, and it's on its way to its next blow up, A1. There's nothing else in between that would change either the trend in the function or the sign of the function. The next obstacle, so to speak, for the function is its next blow up. Because remember, at the AIs, we always have a blow up for the function. On the other side of the blow up, then you come back, again with a positive sign, and you start decreasing. There's nothing, no other event between that blow up and the next fixed point. And the next fixed point, again, you will reach the 0 slope, which is necessary, or which is related to your superstability. After that, you start growing because you had a 0 derivative here. You grow, but not for long, until you hit B2, because at that point you will have a 0 derivative. And again, once that's the case, the sign of the function, not the sign, but the sign of the derivative, I mean, it's still, it turns if all goes well. It's the AI is where the sign of the derivative. So it's the, well, it's f prime that we're talking about here, but we're talking about the history of n prime. See, n prime changes sign there at those points. So whatever its sign was up to this point, it reverses that. So it was positive here, so it becomes negative. So it becomes negative, and there's nothing else that would change the shape of the function. It's heading towards its next blow up like that. So with this arrangement of zeros, this is the general shape of the Newton iteration function that we have constructed. It blows up so at these points, so it runs out of the box. This is very insightful analysis that they picked a fairly general class of functions so that you can still do these graphs without having to pick any specific values for the constants. So everything we're discussing so far is completely general for this class of polynomials, right? All right, so this is interesting. The function is certainly not one-to-one, right? This is not an invertible function. If I pick a value here, for instance, there would be immediately two preimages, one here and one there, for that matter. I could, excuse me, I can even get three preimages if I really want to, three preimages, because in this point, this will be one preimage, this will be second preimage, third one, fourth one, right? So by no means invertible, but that's not my purpose anyway. I just want it to be well-defined, and you see it's well-defined as long as you're not blowing up. So you start playing with this iteration, and we've already found that near the fixed points, right, this zero derivative forces you to get attracted to the fixed points very quickly. So you might start wondering, all right, but can I, given that now I have a graph of the function, can I kind of graphically get at least an estimate for the domain of attraction of the function? And when you start playing with these little things that I've shown here, very soon you come to the realization that you get a safe estimate for the domain of attraction. It's at least as big as what I'm showing now when you do the following. You go to this fixed point, you move to the right and project it down. And this will be a lower bound for the domain of attraction for this fixed point, because when you're here, all right, anything closer than that will very quickly converge. So that's a lower bound. And we call that Z1 plus. And the way to construct that is you simply take this height, which is x1, and you take this particular preimage of the function. There's another preimage there, but we're worrying about this preimage. So it's perfectly well-defined, Z1 plus. Likewise, take the minimum of this dip, which is nearby, and take that to the right and project it down here. That's Z1 minus. This is Z1 plus because I got that from the upper branch, and this is Z1 minus because I got it from the lower branch. And again, suppose that you're just slightly to the left of that, right? Then as you start playing the cobweb game, then very quickly you converge again. So these are certainly good estimates locally for the domain of attraction. You proceed similarly with the other fixed point. Exact same construct. You take this hump, take it to the left and project it to the down, and then take the bump, which is at the fixed point, project it to the right and then go down there, and that gives you Z2 plus and Z2 minus. And again, if you try to play with iterations that fall in this domain, you very quickly see, I can't even draw it anymore. It's so quick, the convergence. So these are domains of attractions for that two fixed point. So certainly when you are in your initial condition is in any one of these, then you're doomed to converge. So if you have any funny behavior, it's not going to be happening in here. It has to be happening outside. Okay. So that brings our attention to the outside. And we also don't want to, get out of the box and start participating in infinite blowups. So it also makes sense that to start restricting our attention to a domain which is bounded away from the location of the blowups. The blowups are here, there, and there. Okay. And again, after a little bit of playing with the cobweb diagram, a natural way of sort of bounding yourself away from it turns out to be the following. Remember this A2 here and the A0 here. Take the images of preimages of A2 and A0 and use those as limits to your domain of investigation. So that's what I'm doing here. Let's start with A2. I can also, come down to this 45-degree line. This is then also A2 right here. So to take the preimages of A2, I can just take this point, which is at the height of A2, and come down here. And that defines a point for me, which I call Y21. I call it Y2, 1 because I get it from A2, and this is the first such point that I'm getting. And again, the construct was simple. Either start from this A2 that I'm showing here, or show A2 here, and just take the first preimage of A2 and come down here. Okay? While you're at it, take the second preimage of A2, also come down here. That gives you Y22. Again, because you started from A2, and this is the second preimage as you're moving to the right. There's no more preimage because you're only hitting these two. Now do the same to A0. Okay, so come here. A0 you can find on the y-axis as well, just by coming down here with A0 and projecting it to the left. Okay, and now take the two preimages of A0, which is always just do the inverse of what you would normally do with the cobweb. What's the cobweb technology? The cobweb technology, pick a point, look above, go up there until you hit the function, and then move to the right until you hit the 45-degree line. Now the inverse of that construct is not invertible. The preimage of construct is do the opposite. So you have a value here, go horizontally until you hit the 45-degree line. Okay? I'm sorry, until you hit the function, and then come down. The 45-degree line is already involved here because I projected it in on down here, right? So I go horizontally and come down here, but that's not, that is the Y01 preimage. Reason being that I'm constructing from A0, and this is the first such point, but I keep moving and find another preimage of A0. That would be Y02. It's still the preimage of A0, but the second one, and I get that by hitting it down here and projecting it down. So, and I'm done. I'm not going to construct more points, but I have this Y21, I have this Z1 plus, I have Y01, Y22, and then I have Z1 minus, Z2 plus, Z2 minus. And these points came out from systematic considerations. Remember, they're not ad hoc. The first one was, this set of points was my brute force estimate for the domain of attraction. And the other one came from this limiting procedure that I really wanted to have. I wanted to work in a bounded domain. I wanted to be in a domain such that if I'm bounded by this, I'm surely not running out of this box. So I'm contained. I don't have to increase the domain of definition of my map. It's enough to be contained. So that motivates then basically being bounded by these larger sets. Now comes the sort of the intuition of finding interesting domains in which you would like to encode the dynamics. I propose to you that the domains of attractions are not interesting. I know exactly what's going to happen in there. The dynamics is very deterministic. Any initial condition that starts in here, the domain of attraction, will be running into the fixed point. So what do you do then? Well, you exclude those. So exclude this and exclude that. And also I've been excluding these points where I run out of the whole box because that's where, you know, the function is heading towards blowups. So there's not much left. It's really just these four sets that are left: I1, I2, I3, I4. Once again, I get this partition by restricting to a bounded domain on which the bounded dynamics takes place without blow up, and I simply take out the domains of attraction. Okay, just by that restriction to the bounded set, I've been taking out these little dots there, and then I also take out the trivial dynamics, which is the two domains of attraction, and then I'm left with these four players. And again, I wrote it out here just to be specific what I1, I2, I3, I4 are, but I can show it to you here. I1 is just this, between two adjacent marked points. Then I have no interest in encoding anything that happens within the domain of attraction of that fixed points. That's boring. So what's the next point, next domain, which is unclear to me a priori? Well, it's this one, right? Just outside the domain of attraction, but bounded away from the blow-up regime, okay? Next one, here. bounded away from the blow-up regime from this direction and hitting the domain of attraction on the other end, right? Then comes the domain of attraction, that's boring. And finally, the only unclear point is here, right? So those are the I1, I2, I3, I4. So it's not ad hoc choice anticipating the results, but that's the only domain in which I can get anything interesting. All the others, I'm either escaping out of this box or I'm going to the fixed point. Now these intervals are my candidates for 4 different states. So I would call them, these are considerations you would do when you do a practical analysis of a system. When would I perceive this iteration complex? I mean, I would submit to you that I have these 4 states, and I would perceive it to be complex if I look at these, just roughly these 4 possible outcomes for the iteration. And I would say that among these 4, it jumps erratically without any obvious pattern. So if that's my anticipation, that I would use these 4 states to encode presumably the dynamics and get that I have presumably a chaotic orbit involving these 4 states. So let's see how that works. At this point, whoops, continue. I'm gearing up first. You know, I will be working with, if this is the game plan, then I will be working with 4 symbols to encode my dynamics, right? That's already clear then, because the minute I pick the number of possible states that I like to use to label my current position and future and past iterations, 4 symbols. The only question is, do I have unrestricted access to any of these to any other, or do I have to work with a transition matrix that tells me what's going on? Let's see that. This is now to show how you construct a transition matrix in a given case. I try to see what the image of the first set is, so that to see the possible transitions. So here's the first set, okay? And the graph of the map over that is just this piece, all right? So the range of the map over the first set varies from A2 down to this point here, okay? So in other words, if I want to show it here, then from this point here up to A2, which is here. Now, I can also show that it's something like that. See, that range contains both I2, I3, and I4, which means that these will be all possible landing locations for me. Once again, the reason is that out of this set, I can get to any one of those others. They're somewhere here, right? So I can basically find the pre-image in this set for every one of those. But the way to see that is that I apply the mapping to the whole interval, and I see which of the 4 targets it contains fully. And I've just shown you that it somehow ranges here. So it contains I2, I3, I4, but it doesn't contain I1. So interestingly, when I start in the first interval, I1, I cannot come back to I1, but I can go to I2, I3, and I4. Okay, so what happens when I start with the second one? Same idea. Here's the second one. And this is the graph of the function over this second one. So I immediately read off the range of the function here. And that range is fairly limited. It's in fact, if I want to understand it, I need to come. This is where the upper point of that interval is mapped, right? So I go to the 45-degree line and map it down here. So the range starts here. Let's remember that. And here's the end point of that I2 interval. I do the same going horizontally and come down here. So the range ends there. So in other words, the range is this. And that range over I2 only contains I1. So from I2, I can not go to I2. I cannot go to I3. I cannot go to I4, but I go to I1. Fairly limited, if you ask me. Seems like a bottleneck. Now, when you do this construct, say go for I3, I can go a bit quicker now. Again, all I do is just, I try to see what the range of the function is over that. So I go up there. Here's the piece of the graph of the function, okay? And I go horizontally like that, get it down, and see it only contains I4. So that's why I've written NI3 contains I4, but not the others. finally, when I do this to I4, now that has a large range, because see, over I4, this is the whole graph of the function. So when I go here, I get the upper end of the range, but when I go here, I get the lower. So altogether, it contains I2, I3, and I4. So from I1, I can go to these. From I2, I can go to this one. For I3, I can go to this one. But I4, I can go to these. There are all sorts of limitations. There's no unlimited access in any of these cases. But what I can do, I can encode what I have. So the transition matrix tells me these are the 4 states. So from I1, I cannot go to I1, right? But I can go to all others. So I write 0, 1, 1, 1, because it's okay to go to the others. For I2, I can only go to I1. So I write 1 for the first part, but then I write 0, 0, 0 for the rest. For I3, my choices are limited. I can only go to I4. So I write 0, 0, 0, 1. And finally, I4 is rich enough, luckily. From I4, I can go to 1, 2, 3. So in the last column, I write 1, 1, 1, but I cannot go to itself. So this has a bunch of zeros. The question is whether this is irreducible or not. The only way to do that is to check. I mean, this is something you could do numerically. You write a loop, and you start multiplying this matrix by itself. I did that multiplication here. The second, the square of that matrix is this. It still has 2 zeros. But the third one is full. So that means that A is irreducible with this K power. What does that mean? It means that even though, amazingly, my options are fairly limited in some cases in 1 iteration, they have increased in 2 iterations. And in 3 iterations, I can reach from any state to any other state. Okay, so under the surface, under a first look, the dynamics is actually fairly rich. That's a good sign. So the symbol space that is my candidate for this analysis, remember that. This is the symbol space here. We already agreed what the number of symbols should be. In this case, this will be 4. And I have a transition matrix which is irreducible. So the theorem was that if I'm able to now, certainly on this space, no further work required for the following statement. On this space, the Bernoulli shift map is chaotic. Done. What I haven't shown is that, in fact, my dynamics can be encoded by this shift map. So I haven't shown yet a one-to-one correspondence between the Newton-Raphson iteration and the Bernoulli shift map. What I have shown that if such a correspondence exists, then the Newton-Raphson iteration is chaotic on this set. Okay, that's what I know. So then how would I go about actually trying to establish, this is the last step. It's actually basically a combination of ideas that we used before. So I go back to the tent map, the logistic map idea for the encoding. So my target will be that I think that this is k equals 3. So if A is irreducible with k equals 3, then the third iterate is full. And I think I have a typo here because I've written that in that case, II intersect n inverse ij is non-zero. But I'm writing that for the first iterate of the map. And for the first iterate, that's not true for any combination. It's only true for the fourth iterate, the third iterate. However, the reason why this is still okay, it's A3ij. Aij non equals 0. Well, I could have written this out for the first iterate and then with this restriction. But what I'm writing here actually doesn't make too much sense because I know for sure that all these entries are non-zero. So I'm not sure what I wanted here. It's good that I'm looking at my own notes, right? So actually, I think at this point, I have to replace the original n with the third iterate of n for this to be correct, right? Because once I work not with the original n, but with the third iterate of n, so I basically concatenate n 3 times. And then when I talk about pre-images, then I'm going to take the pre-image under that map. So here again, this doesn't mean inverse, it just means third pre-image. Yeah, Alex?
So I think at least in my notes it's okay, because instead of n, I've got f. We've defined f as n to the third.
Thank you. So now I know why I did, because I know what I screwed up. Before the class, I said, wait a second, I mixed up the notation because f is the original function whose zeros I'm looking for. But then what I didn't notice is that in the master set of notes, I did note this issue and I renamed n cubed to be f. That's a conflict of notation with the original function, right? That's what I've just realized. So thank you. So I didn't know what I was doing, except that I was creating a conflict of notation. I can fix this here on the fly. I try. At least that forces me to rethink a lot of the things. So I'm just going to say n tilde is the third iterate. Okay. So then what did I do here? Yeah, I've overwritten some of these things, and I think that's coming back at me. So, oh, see, there's f, because that's what I've overwritten. So what do I do here? Like that. And so this will be n tilde, okay? And that's the third iterate. And this is an okay always. That's why I went for the third one. So here's let's understand this statement. I've already used this in another context, this statement. If it's okay for me to go from state I to state J, which is the case, because for the third iterate of the map, which I'm currently considering, I can go from anywhere to anywhere. Then if I ask, what is the intersection of II with the pre-image of ij? Since I can go from II to ij, this is certainly not empty. And the way I will be taking these pre-images, right, is that there will be here sets, I1, I2, and so on, and I will be then going horizontally and projecting them down into these II. So they always will be nice little closed subsets sitting in there, right? And I can do that for any combination I and j once I have passed to this supermap, the third iterate. In this case, all these pre-images will be non-empty. They will be closed because I will never hit the boundary of them. I'm taking the pre-images of closed sets under smooth mappings because I've avoided locations where the map blows up. So any such seed, just take this pre-image of this, project it down. It falls in, that's a little interval. So they will always be connected. I may have several pre-images, but I'm just talking about their intersection with a given interval. There will be just a nice little closed subinterval connected as well. Hence this statement here, where is the statement? Yeah, here's my statement. So it's non-empty, closed, and connected for any set. And remember, this is the fundamental observation that we used for the logistic map, that this was true for any index combination. And this enabled us to do the symbolic encoding. So I'll just use the same procedure that I used there. We just find these multi-indexed sets for any finite combination of the symbols. The only difference here is that for the logistic map, we only allow 2 symbols here. Now, each and every one of these guys can range from 1 to 4. But we define them the same way. This set would be a set which is a finite encoding of symbols, contains a set of symbols with the same finite encoding up to Sn. Namely, I'm shooting for points that are in IS0, because that was the first index here. And their first iterate will be in IS1. Hence, they are currently in the first pre-image of IS1. So I intersect with that. Their second iterate will be in IS2. Hence, they are currently in the second pre-image of IS2. And this is almost correct. I just need to add the tildes here. Okay, and so on. So basically, this set that you see so far contains all the points whose first n elements in the itinerary, and this is actually even n plus 1 for now, agree. all of them. So this is the set of points by construction. When I take this, then I inquire, is this something non-empty, presumably closed, and presumably connected? Because that would help me. It did help in the case of logistic map, of the logistic map. And to see that, remember, we were rewriting these intersections in a funny way, that I would take the first part of the intersection, the first element, and then I start writing the second one, but I always open up new parentheses, right? So when I come to the second preimage, which was here, I've already opened up a parenthesis here where I apply the first preimage, and I'm simply applying that to the first preimage again. That gives me a second preimage, right? So always these opening up these parentheses and using the associative, I guess, property of intersections, because I can take the second preimage as the first preimage of the first preimage. And then I keep opening up new intersections until in the last bit, it's the same construct that we did for the logistic map. I'm faced with the intersection of ISN-1 with the first preimage of ISN. And this is the bit where I can use that elementary observation that we had, that when you take anything like that, it falls in this category that we discussed here, that I know that it's non-empty, closed, and connected. And then I feed that into the next element in this recursive sequence, which again will be in this form. But what I'm feeding in, the outcome of this now takes the role of this one. So again, and it's intersected with ISN-2. So again, the recursive conclusion will be that it's closed, non-empty, and connected, blah, 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 blah. I can go all the way. So as a result of that, this whole set here is closed, non-empty, and connected. It wasn't immediately obvious from here, but from this reformulation and from this elementary observation, which is only true for the third iterate of the map, that's why I'm calling it until that, it is true. So whenever you have that property, you have a very good, you're all set essentially for symbolic encoding, because in this map, in this case, I can then apply Cantor's theorem and take this n go to infinity limit. So what I have is a nested set of connected closed intervals. That would be enough for the existence of the limit, and that would be non-empty by Cantor. But even because they're also connected, that interval is a connected, not an interval, that intersection is connected. The only question is whether that's a point or a finite closed set, because it could still be just a closed interval. Here comes the particular nature of this graph, that this function, as you take preimages, look at it, the derivative is always larger than 1. So in backward time, you will have a uniform bound on the shrinkage in each and every step. Okay, so you have a uniform lower bound and you have a uniform upper bound on the derivative, which is bigger than 1. But for the preimage, what's bigger than 1 becomes less than 1. So it's uniformly bounded away from 1. And for each and every of these branches over each and every of these sets. So basically you can come up with a uniform upper bound on, depending on how you look at it, so a uniform bound on the shrinkage. You must be shrinking at least this much in each and every step, and it's a number. So that means that you cannot have an interval of finite length, because in each and every step you have a Q factor which is shrinking down your preimages down towards 0 without stopping. So the end result of that is that not only is it a connected, not empty intersection of the closed of these nested sets, but it's also a point, not an interval. And that's the result of this shrinkage, the uniform bound, okay, on the function, uniform shrinkage. If it was non-uniform, then you would be out of luck. And in the logistic map, it wasn't clear if it was uniform or not a priori. Why? Because we were working with these two intervals, and over those two intervals, the function had these all sorts of derivatives, you know, starting from 0 to very large. It wasn't a priori clear from the construct. Here, finite pieces immediately clear that I can bound the shrinkage from above and below immediately. Okay, So as a result of that argument, not only is this nested set of growing, well, shrinking in size, but growing in index sets is non-empty, closed, and connected, but because there's this uniform shrinkage, you actually shrink down to a single point, which means that this encoding that you define here and you take to infinity, for any particular admissible symbol sequence, in which case this will be then for the third iterative non-zero, it defines you a unique point. Okay, so that means any symbol in this symbol space has a unique representation. There's a one-to-one correspondence. Again, it's the usual metric that you can use to argue that this mapping that we have just established from the symbol space, well, this is the inverse of that, because I started with the lambda is the physical space, the I1, I2, I3, I4. And this was the symbol space. So this is actually a nice mapping. It's a homeomorphism. It's one-to-one and it's continuous in the metric that we have seen. So we do have a diagram here like this. So it's the space of 4 symbols with this particular transition matrix. And we have the Bernoulli shift map on that one with this transition matrix. We have the symbolic encoding, but here I have to write n tilde, because all this argument was carried out for the third iterative of the map, right? We then have the original statement. This was the theorem that I already listed. But as a result of that, since we do have a conjugacy by this unique encoding to sigma, in terms of, I don't need to check anymore when I use this encoding whether sigma is, one iteration of sigma is the same as one iteration of the mapping, because whenever you encode by itinerary, we've seen that already in 2 examples, that automatically holds. Why? Because the itinerary encodes your future behavior step by step. When you step or you do one more iteration forward, then that whole thing gets shifted towards the past, right? Because already the first symbol encoded or your future, all you have to do is just adjust the present point by 1, push it forward. So I've already done that twice, so I'm not reaching out. So anytime you have an itinerary-based encoding, then automatically the corresponding map in the symbol space that is conjugate to your original map is the Bernoulli shift map. And because you also have invertibility in this case, we can write out this formula for the topological conjugacy. So we're done. So this is a non-trivial example, which is very relevant for real life, because it tells you that in a numerical procedure, if you don't start in the right location, then you might actually be jumping on forever. The reason why that will not happen in practice, or the chances of seeing that is small, and after a while you will not see it. What do you think the reason is? I mean, you may see sustained non-convergence and bad behavior, but over time, presumably, you will go someplace. Why is that? Even though I've just shown, even for this map.
Could it be? Sorry, I'm audible, right?
Yeah, go ahead.
Okay, so could it be that if we are really chaotic, then we will somehow find the area where the numerical error is just so small that we will be just rounded to 0 anyway?
Right. So it's the finite precision. So you're absolutely right. What we have done here is the analysis in a perfect world without any truncation error, right? In real life, there will be a damping factor in this whole procedure, which is the finite precision with which you can represent numbers on a computer. That turns out to have a stabilizing damping effect, right? That doesn't allow arbitrary excursions. So after a while, chances are you will be landing somewhere, but precisely when your precision is very good, so precisely when you're using very high digit arithmetic, right? You're getting very close to this situation. So then you will have a chance to observe this if you don't start in the obvious domains of attraction that we have identified. Okay, so I find this example both insightful for the kind of numerical methods that we keep using, and also it's a nice demonstration of the generalized approach to chaos. It has practically everything in it, right? This generalized definition, the generalized space, multiple symbols, right? And not just 1 or 2, but 4. But also not all transitions are allowed. So we did have to use a transition matrix. But transition matrix wasn't obviously admissible because not all transitions were possible from each state to another state. So we had to work a bit to establish what iterate of the map can be considered as conjugate to the Bernoulli shift map. And we got that the third iterate of the map. But it doesn't matter if the third iterate of the map is just a technical step that technically only the third iterate is conjugate to the shift map, right? It's not that all of a sudden the first and the second iterate will be regular. No, it's just that they're already complicated too. But the third iterate is something I can put my fingers on, that this is exactly the chaotic, exactly the same way as the Bernoulli shift map on this particular space, right? There's that. So any questions about that? All right, so I'll just maybe, I have a few minutes out just to basically write out what I'm going to talk about next, the title and maybe some initial thoughts. This concludes what I wanted to say about chaos and the homework problems, fill in some of the missing details that I stated but didn't actually prove. So the next chapter in this story is Introduction to Hamiltonian Systems. And this is an incredibly important class of systems in multiple areas. It comes up in classical mechanics, it comes up in molecular dynamics, fluid mechanics, also even population dynamics can come up. And that's why it warrants a separate treatment. I mean, these days I don't see it, perhaps because I'm not following that area with the same intensity as I did when I did my PhD thesis. But back then, I mean, there were conferences fully dedicated to Hamiltonian systems. In fact, I still remember first year assistant professor, I went to a conference, which is a very well-attended conference, is Hamiltonian systems with 3 degrees of freedom or more. So it was even more specific, right? It's not even just general Hamiltonian systems, right? And less than infinity. There was tremendous interest then, and a lot of that interest is still being fueled by celestial mechanics. The celestial mechanics problems are to a very good approximation Hamiltonian, because any problem that's a mechanics problem in which the dissipation is practically negligible, all right, is very well approximated by Hamiltonian systems. And when people were asking this question, what's the age of the solar system? They do these long-term calculations. Those are all conservative mechanical system calculations, and they are covered by Hamiltonian formalism, which I'm going to get into. So this can get very abstract very soon, but I'm just gonna follow this the simplest setting, which goes by the name of a canonical Hamiltonian system, because already that's general enough. And I will add finite dimensional, because there's also infinite dimensional extensions. For instance, the wave equation without damping turns out to be an infinite dimensional Hamiltonian system. So what's a canonical Hamiltonian system? It has 2 components, a Q-type variable and a P-type variable. We call these canonically conjugate, and both have the same dimension. Q will be a position-like variable, but this can be a biology problem, so it doesn't have to be position, and P will be a momentum-type variable. But again, it doesn't have to be mechanics. You'll see in a second. Maybe both of them actually refer to positions. But we think of Q as generalized positions and generalized momenta. And the special feature of these systems is there's a scalar function, which depends on, I'll list maybe Q as the first argument, Q, P, and time, okay, which is a mapping from, say, Rn, although, again, this can be defined on a manifold. So Q and P may not be coming from a linear space. In fact, in the most general form, P actually comes from the tangent bundle of the local tangent spaces altogether, not the tangent, the cotangent bundle, which is the space of linear mappings defined as the tangent bundle. It's not like I said, it can get abstract very quickly, which I don't want to get into, but maybe I'll give you a reference. So it's basically a function of 3 arguments in this more general case, q, p, and t. And from that single scalar function, you can reconstruct the whole system, because the first component is just the partial derivative of h with respect to p. And the second is the negative partial of h with respect to q. So this skew symmetry makes it a non-gradient system. So it's not like a gradient system where you would simply have the partial derivatives. And the gradient system is characteristically, it turns out to be dissipated. Hamiltonian systems are characteristically conservative. And what causes that difference is that these 2 derivatives are interchanged, and there's a minus here. If you change them back and remove the minus, that's called a gradient system. And actually the dynamics of a gradient system can be pretty boring. It's mostly going to equilibria attracting, right? Whereas this has incredibly rich dynamics in general. We call the dimension, so n, when this is the case, we call n the degrees of freedom of the Hamiltonian system. And that comes from mechanics, but even we talk about degrees of freedom even if it's not a mechanical problem. It's just simply the n that appears here. Very importantly, every Hamiltonian system is even dimensional. Now, there are conceptual extensions to Hamiltonian systems to odd dimensional spaces, but those are not Hamiltonian systems technically. One needs, but still you can derive them from a function. Those are, but you then need a Poisson bracket to define, and those are somewhat different. So if somebody asks you, I have a three-dimensional fluid motion, is it possible? It looks really regular. Is it possible that it's described by a Hamiltonian system? You will say no, because a three-dimensional fluid motion is three-dimensional, and there's no odd dimensional Hamiltonian system. It might be, it will have other symmetries and interesting properties, but it's not a Hamiltonian system. There's a classic shorthand notation that I will use, and perhaps that's where I'll stop for today. Instead of having to write always these canonical equations, you can just introduce a single variable which will have the q's and p's in it, and that's 2n dimensional. Okay, so that will be the full phase space variable, 2n dimensional. And you introduce a matrix, say J, it's called the canonical symplectic matrix because this turns out to be an interesting geometric structure. It's called a symplectic structure when you this space is, so to speak, endowed with a symplectic structure. I don't want to go into that, but this is, I just wanted to give a name to this. It's called the canonical symplectic matrix. That's a whole area of differential geometry, or study of symplectic forms, that a symplectic form, a differential form, could be used, in fact, to describe the system, and they have beautiful theory by themselves. But this is just the simplest symplectic matrix, so to speak, and it's easy to say what it is. It's the n by n identity and minus n by n identity and 0. So with this machinery, you can rewrite the Hamiltonian system as x dot, okay? And you will take the gradient of h, which will have a q component and a p component. You swap them and you multiply the second one with a minus sign. So that's the same operation as left multiplying that gradient of the Hamiltonian with this matrix, if you think about it. That's exactly what it does. It takes the second component and puts it in of the gradient, puts it in the first row, takes the first component of the gradient, puts it in the second row as here, and adds a negative sign. Okay, so you simply write J. Okay, so that would be a shorthand notation. And I think I'll just stop here. And what I'll do next time, I'll give you several examples of Hamiltonian systems coming from very different areas of mechanics, or even, I think at some point, population geometry, just to motivate why these are important. And then we look at some general properties of Hamiltonian systems. The beauty of that discussion is that immediately you get things for free for this equation without doing any analysis on it. Some really deep conservation laws, symmetry properties that guide your analysis. You know what to expect when you simulate this numerically. You look at a phase portrait or an output that somebody gives you, and immediately you might be able to say you did something wrong because this cannot be possibly the output from a Hamiltonian system. And also, there's a lot of things, normal form theory, which we did, bifurcation theory, which we did in the first part of this course, is when you know that the system is Hamiltonian, a lot of the outcomes are impossible, or there are further simplifications within Hamiltonian normal forms, and a number of things. Any questions? Boy, I was right on time.
Well, maybe if I may, this is not closely related to the Hamiltonian systems, but rather to quantization. In a previous course, I encountered the chaos induced by quantization in control loops, and I never really got my head around there and how does that happen. But still, somehow, if one tries to control like an analog system, a real world system with a computer, and it will only output to the analog digital converter discrete values, and it will somehow induce chaos. And if you can elaborate on that somehow, or if that is that rings a bell, I would be very glad to hear what's behind that, because
chances are that you might look that you were being told about work that I was involved in, because that's that one-dimensional mapping. And I mean, that's a good point. That used to be part of this course. I left it out because it's just too much time to discuss. But basically, it's a good point. You can take a perfectly normal function, which by itself wouldn't even be chaotic, but the discretization dices up that function into little discontinuous increments, right? And those little discontinuous increments, actually, one of your homework problems will be, I think, but even if not, I was alluding to the fact that the binary encoding map is chaotic. Remember, the binary encoding map was actually something like this. And that's already a chaotic mapping. So when you see a structure like this is chaotic, and chaos is sort of robust, not sort of, structurally stable. It turns out these are properties that are structurally stable. So just imagine that taking these and shifting them slightly to each other, right? So still part of this map will be chaotic. And the discretized map that I think you've seen has the property that it would have these little things there. I forgot what it exactly looks like. So whenever you have this little trap, overlapping graphs, that tends to create a little bit of bouncing. And then you can locally encode that with the same ideas that we used here. I don't know how much enlightening this could be, but you very much now have seen all the tools that was involved in that work. I mean, there was a little bit more mathematics added to, to even say give more details about the type of chaos. But these were the same ideas behind. And the building block is is like I said, whenever you see something like that's a chaotic mapping. And I don't know why I've drawn this here. That was irrelevant. Is the 45-degree line, and the binary map already has the property that you just start playing with it. Immediately you will see iterations that are, well, the binary encoding of a number in 0, 1 is chaotic. So that's sort of my way of looking at it, that discretization in many ways is a small deformation of or maybe even large deformation of the encoding map. If the encoding map is chaotic, then the discretization, when you shift these two, you will also find a subset on which it's chaotic. But it has its own, analysis, again, that has a transition matrix, which is not that simple to construct. There will be several states there. You can actually, or in that case, for that, in fact, you can prove that there's a chaotic attractor. So in fact, there's an attracting set into which you go, and within that attracting set, there are all these states which communicate each other in a chaotic fashion. That's a nice example. I'm glad you mentioned that, because I forgot. Yeah, that's another thing that takes some time to present. So I used to do both, and then I settled on this one, just the chaotic iteration.
Yeah, maybe for, I mean, more mathematics focused people, Newton-Raphson is more interesting than a control loop. It could be.
Yeah, you're right. It depends on your taste. Maybe
Yeah.
To an engineer, it's certainly more exciting. And in fact, it was motivated by real observations of positioning errors in robots that nominally, if you consider if you don't consider the discretization from the finite precision and you consider the control loop analog, then it gives you asymptotic stability for that point, right? But if you then in real life you don't have infinite precision in your sensors and actuation and everything, so that nominally asymptotically stable profile breaks up into these little hairs, and those little hairs are able to create micro chaotic behavior. And this was observed in an experiment in which people didn't understand why the robot, whose control circuit is nominally stable and should not be doing this, right, is still oscillating like that. And this was and indeed, you did a macroscopic analysis with the controller, which is a continuous function, or even smooth. It should have been stable, asymptotically stable. And in practice, it wasn't. Yeah. And that was Gabor Stepan's genius insight, that he sort of sat down and just came up with the simplest model for this that captured this and explained this behavior. Who else, if anybody? Okay, looks like we're done for today. So see you tomorrow. We'll be talking more about Hamiltonian systems, more than you ever wanted to know, as was the case about chaos, I guess. Take care. See you tomorrow.